Today, I want to share with you an algorithm problem from AtCoder. I found this problem to be particularly interesting because it's very easy to understand, but reveals many abstract patterns. Before we begin, notice that this video assumes you are familiar with disjoint set data structure, aka union find. So the problem goes like this. On the 2D xy plane, you have two horizontal lines, y equals to 100 and y equals to negative 100. You can think of these lines as the boundaries of a freeway or a track, which is the area between them. Then you have n 1D points scattered on this track. You can think of them as poles or cones, or whatever type of obstacles you like. Now you want to drive a car, the shape of which is a perfect circle, from the far left of the track to the far right of the track, without hitting any of the obstacles. Obviously, whether you are able to do this depends on the size of the circle. If the circle is too large, it won't be able to pass through. This problem is asking you to calculate the maximum size of this circular car such that it's possible for it to pass through this jungle of obstacles. Your algorithm should run on the scale strictly faster than n cubed, where n is the number of obstacles. Pause the video and think about it for a while. I would suggest spending at least 10 minutes before proceeding to the solution, because trying your best to make at least some meaningful observations is how you improve in problem solving. Okay, hopefully you have some thoughts in mind. Here are some common ideas that I've seen people come up with in the past. The first idea is that it seems like the maximum size of the circle depends on minimum distance between any two obstacles. So why don't we calculate the pairwise distances of all obstacles and take the minimum? You may have already figured out that it's not hard to come up with a counterexample to this approach. If, let's say, we only have two obstacles and they are super close to each other. Now, when we calculate minimum pairwise distance, we would get d, the distance between these 2 points. However, in this case, we can easily send a much larger circle to the far right. The second common idea is that what about we do a binary search on the size of the circle? Since we know there must be a threshold where we can no longer send the circle through. The problem with this idea is that it's very hard to simulate the process of sending the circle, because the horizontal range of obstacles might be very large, and the actual path to pass through the obstacles might be very complex and hard to search. So what do we do? Well, there are actually some useful ideas in both approaches. We have to somehow consider the pairwise distances of obstacles, and we also have to try different sizes of the circle. Let's try to combine these two ideas. Let's go back to this pairwise distances graph. What does it look like? Well, can we just think about the dotted lines as solid walls? Can we? Do they behave like solid walls in this problem? Well, if you think about it, whether a line behaves like a solid wall or not depends on the size of the circle passing through it. If the diameter of the circle is less than or equal to the length of this line, then the circle can pass through this wall as if there is no wall at all. But if the diameter of the circle is larger than the length of the line, it cannot pass between the two obstacles, as if there is a solid wall blocking its way. With this observation in mind, let's again go back to the graph of pairwise distances. We now know that if we fix the diameter of the circle to be, let's say, d, then the lines of lengths greater than d would not be effective in blocking the circle. So we might as well just delete those lines. Okay, now what's left on the plane are only those lines that are effective walls for a circle of diameter d. And we can see that it's possible to move the circle from the left side to the right side. In fact, in this graph of effective walls, as long as the upper boundary is not connected to the lower boundary, we can always send the circle through. On the contrary, if the upper boundary is connected to the lower boundary, we cannot send the circle through. So now the problem becomes finding the maximum diameter of the circle such that in the corresponding graph of effective walls, upper boundary and the lower boundary are disconnected. It is possible to do a binary search on the diameter at this point, but there is a more straightforward method. Notice that as we decrease the diameter of the circle, there would be more and more walls going out of effect. This process is monotonic, meaning that walls, or edges, of greater lengths are deleted first. This is another key observation. Since we have captured the abstract structure of this problem, let's reformulate it. The relationships of obstacles can be represented as an undirected graph. There are two special nodes representing the upper and lower boundaries of the track. Other nodes represent obstacles. The weighted edges represent pairwise Euclidean distances between obstacles. For simplicity on this picture, just think of the actual lengths of the lines as the edge weights. We want to delete the longest edge in the graph until we disconnect the two red nodes. You can think of this process as gradually decreasing the diameter of the circle and building the corresponding graph of effective walls. The last edge we deleted before disconnecting the red nodes is the answer to the original problem. Because if the diameter of the circle is even slightly bigger, this last edge cannot be deleted, and it would connect the two boundary nodes, which makes it impossible for the circle to pass. But how do we implement this? This seems like a reversed union find process. We are disconnecting sets instead of joining them. Well, if we think one step deeper, we can actually discover that this problem can be solved the other way around. Instead of deleting edges until we disconnect the two boundary nodes, we can add edges until we connect the two boundary nodes. And the last edge we edit will be the final answer to our problem. Because if we increase the diameter even just a little bit, we would have to add this last edge into the graph, connecting the boundary nodes and making it impossible for our circle to pass. This is actually a perfect example of the so-called strong duality, where optimizations from opposite directions will eventually yield the same answer. No matter if you delete edges from the original graph in descending order, or adding edges to the empty graph in ascending order, you would end up discovering the same edge as your final answer. In summary, the implementation of the final algorithm goes like this. We first build the complete graph of pairwise Euclidean distances of obstacles and boundaries. Then we sort all the edges based on their weights. After that, we initialize a unifying data structure and use edges in ascending order to merge nodes until we connect the two boundary nodes. Then we take the last edge we used as the final answer. The dominating term of the runtime is sorting the edges, which takes n squared log n, because the number of edges is on the order of n squared. I think a high-level takeaway from this problem would be that the first step of problem solving should always be trying to extract the abstract patterns of a problem. At first glance, this problem seems to be a pretty complicated computational geometry problem. But it turns out we can transform it into a graph problem and solve it using a simple step of union find. Alright, if you enjoyed this, remember to click subscribe as I will upload more fun exercises like this in the future. Below, I've included the link to the original problem. You can try to submit your solution. See you soon.